So today's lecture is on sorting. We'll be talking about specific sorting algorithms today. I want to start by motivating why we're interested in sorting, which should be fairly easy. And then I want to discuss a particular sorting algorithm that's called insertion sort. That's probably the simplest sorting algorithm you can write. It's 5 lines of code. It's not the best sorting algorithm that's out there, and so we'll try and improve it. And we'll also talk about merge sort, which is a divide and conquer algorithm. And that's going to motivate the last thing that I want to spend time on, which is recurrences and how you solve recurrences. And typically, the recurrences that we'll be looking at in 006 are going to come from divide and conquer problems like merge sort, but you'll see this over and over. So let's talk about why we're interested in sorting. Now, there's some fairly obvious applications, like if you want to maintain a phone book, you got a bunch of names and numbers corresponding to a telephone directory, and you want to keep them in sorted order so it's easy to search. MP3 organizers, spreadsheets, etc. So there's lots of obvious applications. There's also some interesting problems that become easy once items are sorted. And one example of that is finding a median, for example. So let's say that you have a bunch of items in an array A0 through n, and A0 through n contains n numbers, and they're not sorted. When you sort, you turn this into B0 through n, where if it's just numbers, then you may sort them in increasing order or decreasing order. Let's just call it increasing order for now. Or if they're records and they're not numbers, then you have to provide a comparison function to determine which record is smaller than another record. And that's another input that you have to have in order to do the sorting. So it doesn't really matter what the items are, as long as you have the comparison function. Think of it as less than or equal to. And if you have that, and it's just straightforward, obviously to check that 3 is less than 4, etc. But it may be a little more complicated for more sophisticated sorting applications. But the bottom line is that if you have your algorithm that takes the comparison function as an input, you're going to be able to go, after a certain amount of time, get B0n. Now, if you wanted to find the median of the set of numbers that were originally in the array A, what would you do once you have the sorted array B? Yep?
Isn't there a more efficient algorithm for median?
Oh, absolutely. But there's, this is sort of a side effect of having a sorted list. If you happen to have a sorted list, there's many ways that you could imagine building up a sorted list. One way is you have something that's completely unsorted and you run insertion sort or merge sort. Another way would be to maintain a sorted list as you're getting items put into the list. Okay? So if you happen to have a sorted list and you need to have the sorted list for some reason, the point I'm making here is that finding the median is easy. Okay? And it's easy because all you have to do is to go look at, depending on whether n is odd or even, look at b of n over 2, right? That would give you the median, because you'd have a bunch of numbers that are less than that, and the equal set of numbers that are greater than that, which is the definition of median. All right? So this is not necessarily the best way, as you pointed out, of finding the median, but it's constant time if you have a sorted list. All right? That's the point I wanted to make. There are other things that you could do, and this came up in Eric's lecture, which is the notion of binary search. finding an element in an array, a specific element. You have a list of items, again, A, 0 through n, and you're looking for a specific number or item. You could obviously scan the array, and that would take you linear time to find this item. If the array happened to be sorted, then you can find this in logarithmic time using what's called binary search. Okay? And binary search, let's say you're looking for a specific item, let's call it k. Binary search, roughly speaking, would work like you go compare k to, again, b of n over 2, and decide, given that b is sorted, you get to look at 1/2 of the array. If b of n over 2 is not exactly k, then, well, if it's exactly k, you're done. Otherwise, you look at the left half, you do your divide and conquer paradigm, and you can do this in logarithmic time. All right? So keep this in mind, because binary search is going to come up in today's lecture and again in other lectures. It's really a great paradigm of divide and conquer, probably the simplest, and it essentially takes something that's linear, a linear search, and turns it into logarithmic search. So those are a couple of problems that become easy if you have a sorted list, and there's some not so obvious applications of sorting. For example, data compression. If you wanted to compress a file, one of the things that you could do is to, and it's a set of items, you could sort the items, and that automatically finds duplicates, and you could say, if I have 100 items that are all identical, I'm going to compress the file by representing the item once and then having a number associated with the frequency of that item, similar to what document distance does. Document distance can be viewed as a way of compressing your initial input. Obviously, you lose the works of Shakespeare or whatever it was, and it becomes a bunch of words and frequencies. But it is something that compresses the input and gives you a different representation. And so people use sorting as a subroutine in data compression. Computer graphics uses sorting. Most of the time, when you render scenes in computer graphics, you have many layers corresponding to the scenes. It turns out that in computer graphics, most of the time, you're actually rendering front to back, because when you have a big opaque object in front, you want to render that first, so you don't have to worry about everything that's occluded by this big opaque object, and that makes things more efficient. And so you keep things sorted front to back most of the time in computer graphics rendering. But some of the time, if you're worried about transparency, you have to render things back to front. So typically, you have sorted lists corresponding to the different objects in both orders, both increasing order and decreasing order, and you're maintaining that. So sorting is a real important subroutine in pretty much any sophisticated application you look at. So it's worthwhile to look at the variety of sorting algorithms that are out there. And we're going to do some simple ones today. But if you go and look at Wikipedia and do a Google search, there's all sorts of sorts, like cocktail sort and bitonic sort and what have you. And there's reasons why each of these sorting algorithms exists, because in specific cases, they end up winning on types of inputs or types of problems. All right? So let's take a look at our first sorting algorithm. I'm not going to write code, but it will be in the notes, and it is in your document distance Python files. But I'll just give you pseudocode here and walk through what insertion sort looks like, because the purpose of really describing this algorithm to you is to analyze its complexity. If you need to do some counting here with respect to this algorithm, to figure out how fast it's going to run and what the worst case complexity is. So what is insertion sort? For I equals 1, 2 through n, given a sorted, given an input to be sorted, what we're going to do is we're going to insert a of I in the right position, and we're going to assume that we are sort of midway through the sorting process where we have sorted a 0 through I minus 1, and we're going to expand this to this array to have I plus 1 elements, and a of I is going to get inserted into the correct position. And we're going to do this by pairwise swaps down to the correct position for the number that is initially in A of I. All right? So let's go through an example of this. We're going to sort in increasing order. Just have 6 numbers. And initially we have 5, 2, 4, 6, 1, 3. And we're going to take a look at this. And you start with the index 1 or the second element, because the very first element, it's a single element and it's already sorted by definition. But you start from here, and this is what we call our key. And that's essentially a pointer to where we're at right now. And the key keeps moving to the right as we go through the different steps of the algorithm. And so what you do is you look at this, and you have this is A of I. That's your key. And you have A of 0 to 0, which is 5. And this, since we want to sort in increasing order, this is not sorted. And so we do a swap. So what this would do in this step is to do a swap. And we would go obtain 2, 5, 4, 6, 1, 3. So all that's happened here in this step, in the very first step where the key is in the second position, is one swap happened. Now your key is here at item 4. Again, you need to put 4 into the right spot. And so you do pairwise swaps. And in this case, you have to do one swap, and you get 2, 4, 5. And you're done with this iteration. So what happens here is you have 2, 4, 5, 6, 1, 3. And now the key is over here at 6. Now at this point, things are kind of easy in the sense that you look at it and you say, well, 6 is, I know that this part is already sorted. 6 is greater than 5, so you have to do nothing. So there's nothing, there's no swaps that happen in this step. So all that happens here is you're going to move the key to one step to the right. So you have 2, 4, 5, 6, 1, 3, and your key is now at 1. Here you have to do more work. Now you see one aspect of the complexity of this algorithm, given that you're doing pairwise swaps. The way this algorithm was defined in pseudocode out there was I'm going to use pairwise swaps to find the correct position. So what you're going to do is you're going to have to swap first 1 and 6, and then you'll swap 1 is over here, so you'll swap this position and that position, and then you'll swap, essentially do 4 swaps to get to the point where you have 1, 2, 4, 5, 6, 3. So this is the result. 1, 2, 4, 5, 6, 3. And the important thing to understand here is that you've done 4 swaps to get 1 to the correct position. Now you can imagine a different data structure where you move this over there and you shift them all to the right. But in fact, that shifting of these 4 elements is going to be computed in our model as 4 operations, or 4 steps anyway. So there's no getting away from the fact that you have to do 4 things here, and the way insertion sort, or the code that we have for insertion sort, does this is by using pairwise swaps. So we're almost done. Now we have the key at 3, and now 3 needs to get put into the correct position, and so you've got to do a few swaps. This is the last step. And what happens here is 3 is going to get swapped with 6, and then 3 needs to get swapped with 5, and then 3 needs to get swapped with 4, and then since 3 is greater than 2, you're done. So you have 1, 2, 3, 4, 5, 6. Okay. And that's it. So analysis. How many steps do I have? Yep. No, and how many steps do I have? I guess that wasn't a good question. If I think of a step as being a movement of the key, how many steps do I have? I have theta n steps, and in this case, you can think of it as n minus 1 steps since you started with 2. But let's just call it theta n steps in terms of key positions. And you're right, it is n square, because at any given step, it's quite possible that I have to do theta n work. And one example is this one right here, where I had to do 4 swaps. And in general, you can construct a scenario where towards the end of the algorithm, you'd have to do theta n work. But if you had a list that was reverse sorted, you would essentially have to do, on an average, n by 2 swaps as you go through each of the steps, and that's theta n. So each step is theta n swaps. Okay? And when I say swaps, I could also say each step is theta n compares and swaps. All right? And this is going to be important because I'm going to ask you an interesting question in a minute. But let me summarize. What I have here is a theta n square algorithm. The reason this is a theta n square algorithm is because I have theta n steps, and each step is theta n. When I'm counting, what am I counting in terms of operations? The assumption here, unspoken assumption, is being that an operation is a compare and a swap, and they're essentially equal in cost. Okay? And in most computers, that's true. You have a single instruction in, say, the x86 or the MIPS architecture that can do a compare, and the same thing for swapping registers. So perfectly reasonable assumption that compares and swaps for numbers have exactly the same cost. But if you had a record and you were comparing records, and the comparison function that you use for the records was in itself a method call or a subroutine, it's quite possible that all you're doing is swapping pointers or references to do the swap, but the comparison could be substantially more expensive. Okay? For most of the time, and we'll differentiate if it becomes necessary, we're going to be counting comparisons in the sorting algorithms that we'll be putting out. And we'll be assuming that either compares and swaps are roughly the same, or that compares are, and we'll say which one, of course, or that compares are substantially more expensive than swaps. Okay, so if you had either of those cases for insertion sort, you have a theta n square algorithm. All right, you have theta n square compares and theta n square swaps. Now, here's the question. Let's say that compares are more expensive than swaps. And so I'm concerned about the theta n square comparison cost. I'm not as concerned, because of the constant factors involved, with the theta n square swap cost. All right? What's a simple, this is a cushion question. Okay, this, what's a simple fix, change to this algorithm that would give me a better complexity in the case where compares are more expensive, or I'm only looking at the complexity of compares, so the theta whatever of compares, right? Anyone? Yeah, back there. You could compare it with the middle. What did I call it? I called it something. What you just said, I called it something. Yeah, I saw you first. Binary search, that's right. 2 cushions for this one. All right, so you pick them up after lecture. So you're exactly right. You got it right. I called it binary search up here. Okay, and so if you can take insertion sort and you can sort of trivially turn it into a theta n log n algorithm if you're talking about n being the number of compares. Okay, and all you have to do that is to say, you know what, I'm going to replace this with binary search. And you can do that, and that was the key observation, that because a of 0 through I minus 1 is already sorted, right? And so you can do binary search on that part of the array. And so let me just write that down. Do a binary search on a of 0 through I minus 1, which is already sorted. And essentially, you can think of it as theta log I time, and for each of those steps, and so then you get your theta n log n. But okay, now why can't I theta log n in terms of compares? Does this help the swaps for an array data structure? No, because binary search will require insertion into a of 0 through I minus 1, right? So here's the problem. Why don't we have a full-fledged theta n log n algorithm regardless of the cost of compares or swaps? We don't quite have that, right? We don't quite have that because we need to insert our a of I into the right position into a of 0 through I minus 1. When you do that, if you have an array structure, it might get into the middle, and you have to shift things over to the right. And when you shift things over to the right, in the worst case, you may be shifting a lot of things over to the right, and that gives back to worst case complexity of theta n. Okay? So a binary search in insertion sort gives you theta n log n for compares, but it's still theta n squared for swaps. All right? Okay, good. So as you can see, there's many varieties of sorting algorithms. We just looked at a couple of them. And they were both insertion sort. The second one that I just put up is, I guess, technically called binary insertion sort because it does binary search. And the vanilla insertion sort is the one that you have the code for in the docdist program, or at least one of the docdist files. So let's move on and talk about a different algorithm. So what we'd like to do now, this class is about constant improvement, right? We're never happy. We always want to do a little bit better, right? And eventually, once we run out of room from an asymptotic standpoint, you take these other classes where you try and improve constant factors and get 10% and 5% and 1% and so on and so forth. But we'll stick to improving asymptotic complexity, and we're not quite happy with binary insertion sort, because in the case of numbers, our binary insertion sort has theta n square complexity if you look at swaps, right? So we'd like to go find an algorithm that is theta n log n, and then I guess eventually we'll have to stop, but Eric will take care of that. There's a reason to stop. It's when you can prove that you can't do any better, right? And so we'll get to that eventually. So merge sort is also something that you've probably seen, but there'll probably be a couple of subtleties that come out as I describe this algorithm that hopefully will be interesting to those of you who already know merge sort. And those of you who don't, it's a very pretty algorithm. It's a standard recursion recursive algorithm, similar to a binary search. What we do here is we have an array A. We split it into two parts, L and R. And essentially, we kind of do no work, really, in terms of the L and R, in the sense that we keep splitting, and all the work is done down at the bottom in this routine called merge, where we are merging a pair of elements at the leaves, and then we merge two pairs and get 4 elements, and then we merge four tuples of elements, etc., and go all the way up. So while I'm saying L turns into L prime out here, there's no real explicit code that you can see that turns L into L prime. It happens really later. There's no real sorting code here. It happens in the merge routine. And you'll see that quite clearly when we run through an example. So you have L and R turn into L prime and L prime and R prime. And what we end up getting is a sorted array A, and we have what's called a merge routine that takes L prime and R prime and merges them into the sorted array. So at the top level, what you see is split into two and do a merge and get to the sorted array. The input is of size n. You have two arrays of size n over 2. These are two sorted arrays of size n over 2. And then finally, you have a sorted array of size n. So if you want to follow the recursive execution of this in a small example, then you'll be able to see how this works, and we'll do a fairly straightforward example with 8 elements. So at the top level, before we get there, merge is going to assume that you have two sorted arrays and merge them together. That's the invariant in merge sort, or for the merge routine. It assumes the inputs are sorted, L and R, actually I should say L prime and R prime. So let's say you have 20, 13, 7, and 2. You have 12, 11, 9, and 1. And this could be L prime, and this could be R prime. What you have is what we call a two-finger algorithm. And so you got 2 fingers, and each of them point to something. And in this case, one of them is pointing to L. My left finger is pointing to L prime, or some element in L prime. My right finger is pointing to some element in R prime. And I'm going to compare the 2 elements that my fingers are pointing to. And I'm going to choose, in this case, the smaller of those elements. And I'm going to put them into the sorted array. OK, so start out here. I look at that. And I compare 2 and 1. And which is smaller? 1 is smaller. So I'm going to write 1 down. So this is a two-finger algo for merge, and I put 1 down. When I put 1 down, I have to cross out 1. So effectively, what happens is, let me just circle that instead of crossing it out, and my finger moves up to 9. Okay, so now I'm pointing at 2 and 9, and I repeat this step. All right, so now in this case, 2 is smaller, so I'm going to go ahead and write 2 down, and I can cross out 2 and move my finger up to 7. All right, and so that's it. I won't bore you with the rest of the steps. It's essentially walking up. You have a couple of pointers, and you're walking up these 2 arrays, and you're writing down 1, 2, 7, 9, 11, 12, 13, 20. Okay? And that's your merge routine. And all of the work, really, is done in the merge routine. Because other than that, the body is simply a recursive call. I mean, you have to obviously split the array, but that's fairly straightforward. if you have an array, A is 0 through n, then depending on whether n is an odd or even, you can imagine that you set L to be A 0 n by 2 minus 1, and R similarly. And so you just split it halfway in the middle, and I'll talk about that a little bit more. There's a subtlety associated with that we'll get to in a few minutes. But to finish up in terms of the computation of merge sort, this is it. The merge routine is doing most, if not all, of the work. And this two-finger algorithm is going to be able to take two sorted arrays and put them into a single sorted array by interspersing or interleaving these elements. And what's the complexity of merge? If I have two arrays of size n over 2 here, what do I have? Yeah. N. All right. We'll give you a cushion too. Theta n complexity. So far so good. It's a little. I know you know the answer as to what the complexity of merge sort is, but I'm guessing that most of you won't be able to prove it to me because I'm kind of a hard guy to prove something to. Anyway, and I can always say no, I don't believe you or I don't understand, right? So it's the complexity, and you've said this before in class, and I think Eric's mentioned it. The overall complexity of this algorithm is theta n log n, okay? And where does that come from? How do you prove that? And so what we'll do now is take a look at merge sort, and we'll look at a recursion tree, and we'll try and, there are many ways of proving that merge sort is theta n log n. The way we're going to do this is what's called proof by picture. And it's not an established proof technique, but it's something that is very helpful to get an intuition behind the proof and why the result is true, right? So, and you can always take that and you can formalize it and make this something that everyone believes. And we'll also look at substitution, possibly in section tomorrow, for recurrence solving. So where we're at right now is that we have a divide and conquer algorithm that has a merge step that is theta n. And so if I just look at this structure that I have here, I can write a recurrence for merge sort that looks like this. So when I say complexity, I can say T of n, which is the work done for n items, is going to be some constant time in order to divide the array. So this could be the part corresponding to dividing the array. And there's going to be two problems of size n over 2. And so I have 2t of n over 2. And this is the recursive part. And I'm going to have c times n, which is the merged part. Okay? And that's some constant times n, which is what we have here with respect to the theta n complexity. So you have a recurrence like this, and I know some of you have seen recurrences in 6042, and you know how to solve this. What I'd like to do is show you this recursion tree expansion that not only tells you how to solve this recurrence, but also gives you a means of solving recurrences where instead of having c of n, you have something else out here. You have f of n, which is a different function from the linear function. And this recursion tree is, in my mind, the simplest way of arguing the theta n log n complexity of merge sort. Right, so what I want to do is expand this recurrence out. And let's do that over here. So I have c of n on top. I'm going to ignore this constant factor because c of n dominates. So I just start with c of n. I want to break things up as I do the recursion. So when I go C of n at the top level, that's the work I have to do at the merge at the top level. And then when I go down to two smaller problems, each of them is size n over 2. So I do C times n, excuse me, divided by 2 work. So this is just a constant C. It just represents, I don't want to write thetas up here. You could. And I'll say a little bit more about that later. But think of this Cn as representing the theta n complexity. And C is this constant. So C times n here, C times n over 2 here. And then when I keep going, I have C times n over 4, C times n over 4, etc. And so on and so forth. And when I come down all the way here, n is eventually going to become 1, or essentially a constant. And I'm going to have a bunch of C's here. All right? So here's another question that I'd like you to answer. Someone tell me what the number of levels in this tree are precisely, and the number of leaves in this tree are precisely. Yeah?
Number of levels is log n plus 1.
Log n plus 1, log to the base 2 plus 1. Yeah, and the number of leaves? Yeah, you raised your hand back there first. Number of leaves?
I think n.
Yeah, you're right. You think right. Okay, so 1 plus log n and n leaves. All right? When n becomes 1, how many of them do you have? You're down to a single element, which is by definition sorted, and you have n leaves. Right? So now let's add up the work. Right? So this is, I really like this picture because it's just so intuitive in terms of getting us the result that we're looking for. Right? So you add up the work in each of the levels of this tree. All right? So the top level is Cn. The second level is Cn, because I added half and half. Cn. Cn. Wow. What symmetry. Okay? So you're doing the same amount of work modulo the constant factors here with what's going on with the C1, which we've ignored, but roughly the same amount of work in each of the levels, right? And now you know how many levels there are. It's 1 plus log n. So if you want to write an equation for T of n, it's 1 plus log n times C of n, which is theta of n log n. All right? So I've mixed in constant C and thetas. For the purposes of this description, they're interchangeable. You will see recurrences that look like this in class. And things like that. Don't get confused. It's just a constant multiplicative factor in front of the function that you have. And it's just a little easier, I think, to write down these constant factors and realize that the amount of work done is the same in each of the leaves. And once you know the dimensions of this tree in terms of levels and in terms of the number of leaves, you get your result. All right? So we've looked at 2 algorithms so far. And insertion sort, if you talk about numbers, is theta n squared for swaps. Merge sort is theta n log n. Here's another interesting question. What is one advantage of insertion sort over merge sort? Yeah?
You can store it in place.
What does that mean?
You don't have to move elements outside of the memory that are already in there.
That's exactly right. That's exactly right. So the 2 guys who answered the questions before with the levels and you, come to me after class. So that's a great answer. It's in-place sorting is something that has to do with auxiliary space. And so what you see here, and it was a bit hidden here, but the fact of the matter is that you had L prime and R prime, and L prime and R prime are different from L and R, which were the initial halves of the inputs to the sorting algorithm, right? And what I said here is we're going to dump this into A. That's what this picture shows. This says sorted array A. And so you had to make a copy of the array in the two halves L and R in order to do the recursion, and then to take the results and put them into the sorted array A. So you needed, in merge sort, you needed theta n auxiliary space. So merge sort, you need theta n extra space. And the definition of in-place sorting implies that you have theta 1 constant auxiliary space. Okay? The auxiliary space for insertion sort is simply that temporary variable that you need when you swap two elements. Right? So when you want to swap a couple of registers, you've got to store one of the values in a temporary location, overwrite the other, et cetera. And that's the theta 1 auxiliary space for insertion sort. So there is an advantage of the version of insertion sort we've talked about today over merge sort. And if you have a billion elements, that's potentially something you don't want to store in memory. If you want to do something really fast and do everything in cache or main memory, and you want to sort billions or maybe even trillions of items, this becomes an important consideration. I will say that you can reduce the constant factor of the theta n. So in the vanilla scheme, you could imagine that you have to have a copy of the array. So if you had n elements, you essentially have n extra items of storage. You can make that n over 2 with a simple coding trick by keeping 1/2 of A. You can sort of throw away one of the L's or one of the R's, and you can get it down to n over 2. And that turns out it's a reasonable thing to do if you have a billion elements and you want to reduce your storage by a constant factor. So that's one coding trick. Now, it turns out that you can actually go further, and there's a fairly sophisticated algorithm that's sort of beyond the scope of 6006. That's an in-place merge sort. And this in-place merge sort is kind of impractical in the sense that it doesn't do very well in terms of the constant factor. So while it's in place and it's still theta n log n, the problem is that the running time of an in-place merge sort is much worse than the regular merge sort that uses theta n auxiliary space. So people don't really use in-place merge sort. It's a great paper. It's a great thing to read. Its analysis is a bit sophisticated for 006, so we won't go there. But it does exist. So you can take merge sort, and I just want to let you know that you can do things in place. In terms of numbers, some experiments we ran a few years ago, so these may not be completely valid because I'm going to actually give you numbers. But merge sort in Python, if you write a little curve fit program to do this, is 2.2 n log n microseconds, okay, for a given n, right? So this is the merge sort routine. And if you look at insertion sort in Python, that's something like 0.2 n square microseconds. Okay? So you see the constant factors here. If you do insertion sort in C, which is a compiled language, then it's much faster. It's about 20 times faster. It's 0.01 n square microseconds. Okay? So a little bit of practice on the side. We do ask you to write code, and this is important. The reason we're interested in algorithms is because people want to run them. And what you can see is that you can actually find an n. So regardless of whether you're Python or C, this sort of tells you that asymptotic complexity is pretty important. because once n gets beyond about 4,000, you're going to see that merge sort in Python beats insertion sort in C. Right? So the constant factors get subsumed beyond certain values of n. So that's why asymptotic complexity is important. You do have a factor of 20 here, but that doesn't really help you in terms of keeping an n-square algorithm competitive. It stays competitive for a little bit longer, but then falls behind. All right? OK, so that's what I wanted to cover for sorting. So hopefully you have a sense of what happens with these two sorting algorithms. We'll look at a very different sorting algorithm next time using heaps, which is a different data structure. The last thing I want to do in the couple of minutes I have left is give you a little more intuition as to recurrence solving based on this diagram that I wrote up there. And so we're going to use exactly this structure, and we're going to look at a couple of different recurrences that I won't really motivate in terms of having a specific algorithm, but I'll just write out the recurrence, and we'll look at the recursion tree for that, and I'll try and tease out of you the complexity associated with these recurrences, or the overall complexity. So let's take a look at T of n equals 2t of n over 2 plus cn squared. Okay, c times n squared. All right, let me just call that cn. No need for the brackets. So constant c times n squared. So if you had a crummy merge routine and it was taking n squared and you coded it up wrong, that would be, it's not a great motivation for this recurrence, but it is a way this recurrence could have come up. All right, so what does this recursive tree look like? Well, it looks kind of the same, obviously. You have cn squared. You have cn squared divided by 4, cn squared divided by 4, cn squared divided by 16, 4 times. Looking a little bit different from the other one. The levels and the leaves are exactly the same. Eventually, n is going to go down to 1. So you will see c all the way here. And you're going to have n leaves. And you will have, as before, 1 plus log n levels. Everything is the same. Right? And this is why I like this recursive tree formulation so much, because now all I have to do is add up the work associated with each of the levels to get the solution to the recurrence. Right? Now take a look at what happens here. cn squared divided by 2. cn squared divided by 4. And this is n times c. Right? So what does that add up to? Yeah.
Bounded by 2cn squared, right?
Yeah, exactly. Exactly right. So if you look at what happens here, this dominates. All of the other things are actually less than that. Okay? And you said bounded by 2cn squared because this part is bounded by cn squared, and I already have cn squared up at the top. Right? So this particular algorithm that corresponds to this crummy merge sort, or wherever this recurrence came from, is a theta n square algorithm. And in this case, all of the work done is at the root, at the top level of the recursion. Okay? Here, there was a roughly equal amount of work done in each of the different levels. All right? Here, all of the work was done at the root. Okay? And so to close up shop here, let me just give you real quick a recurrence where all of the work is done at the leaves, just for closure. So if I had magically a merge routine that actually happened in constant time, either through buggy analysis or because it was buggy, then what does the tree look like for that? And I can think of this as being theta 1, or I can think of this as being just a constant c. I'll stick with that. So I have c, 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 and whoa, I tried to move that up. That doesn't work. So I have n leaves as before, And so if I look at what I have here, I have C at the top level, I have 2C, and so on and so forth, 4C, and then I go all the way down to NC. All right? And so what happens here is this dominates. And so in this recurrence, the whole thing runs in theta n. So what the solution to that is theta n. And what you have here is all of the work being done at the leaves. All right? We're not going to really cover this theorem that gives you a mechanical way of figuring this out, because we think the recursive tree is a better way of looking at it. But you can see that depending on what that function is, in terms of the work being done in the merge routine, you'd have different versions of recurrences. All right? I'll stick around, and people who answered questions, please pick up your cushions. See you next time.